Good morning students. Today I am going to take about the lesson number 6. Is nothing but gaseous state. Okay. Gaseous state is nothing but the we are going to learn about all the gases which is exist in nature. Okay. Let's see the introduction. Take the page number of 159. 6.1 introduction. We can survive for weeks without food, days without water, but only minutes without air. Thus we inhale a lungful of air every few seconds. Keep some of the molecules for our own age and some of the molecules that our body no longer takes, and exhale the mixture back into the surrounding air. The air around us is in the gaseous state, which is the simplest of the states of matter. Although the chemical behavior of gases depends on the composition of the gases. All the gases have remarkably similar physical behavior. The gases exist in nature. It has a similar physical behavior. Okay. Earth is surrounded. Do you know the difference between gas and vapor? Gas is a substance that is normally in a gaseous state at room temperature and 1 atmospheric pressure, while a vapor is a gaseous form of any substance that is liquid or solid at room temperature and 1 atmospheric pressure. The difference between gases and vapor is nothing but gas is a substance that is normally in a gaseous state at a room temperature and 1 atmospheric pressure. Vapor is nothing but the gaseous form of any substance like a water, okay, that is liquid or solid at room temperature and 1 atmospheric pressure. Earth is surrounded by an atmosphere of air. Most composition in volume percentage is roughly 78% of nitrogen. We have 78% of nitrogen, 21% of oxygen, and 1% of other gases like helium gases or other gases. Okay, gases of the known elements, only 11 are gases under normal atmospheric condition. Of the known elements, only 11 gases are under normal atmospheric conditions. The elements hydrogen, nitrogen, oxygen, fluorine and chlorine exist as gaseous diatomic molecules. Diatomic means is nothing but two molecules. Okay, two elements coming to form a single molecule. The two elements will be H2, N2, Cl2. These are called as diatomic molecules. These are exist in a gaseous state. Okay, as a gaseous diatomic molecule. Another form of the oxygen, namely ozone, is also a gas at room temperature. The another allotropic form of oxygen is nothing but ozone. It is also exists in a gaseous state at room temperature. The noble gases, namely helium, neon, argon, krypton, xenon, radon, of 18th group of monoatomic gases, and also the noble gases also exist in a gaseous state, that is called as inert gases. Okay, the name of inert gases is helium, neon, argon, krypton, xenon, radon. Okay, these are noble gases. It will not react with another compound because it has a stable electronic configuration, that is NS2 and NP6. Noble gases is nothing but helium, neon, argon, krypton, xenon and radon. Okay, these are called as noble gases. It is also exists in a gaseous state and it does not react with any other compound because it has a stable configuration. Stable configuration is nothing but it has a NS2 and NP6 configuration. NS2 and NP6 configuration. Okay. These gases are called as monoatomic gases because it does not link with any other atom or elements. Compounds such as a carbon monoxide, carbon dioxide, nitrogen dioxide, nitric oxide also exist in the gaseous state under normal atmospheric condition. Compounds like CO, carbon monoxide, and CO2, carbon dioxide, nitrogen dioxide, nitric oxide also exist in a gaseous state at normal conditions. In this unit, we learn related phenomena. Let's see the gas laws. The gas laws have played a major role in the development of chemistry. The physical properties of all gases are governed by the gas law that were formulated based on the studies of the properties like pressure, volume, etc. The gases contain the properties like pressure and volume, etc. also temperature. As a function of temperature, before studying the gas law in detail, let us understand the important parameter, namely the pressure. What is the pressure? Before studying the above gases, you should know what is the pressure. Okay. Pressure is defined as a force divided by the area to which a force is applied. The SI unit of pressure is called as a Pascal, which is defined as a 1 Newton per square meter. That is Newton meter per minus. There are the other units that are commonly used and related with the SI unit as follows. Pressure has a formula that is force divided by area. Nothing but the formula of pressure. Okay. Pressure, the formula of pressure is nothing but pressure equal to force divided by area. It depends on the area which applied a force. Okay. Let's see. The SI unit of force is nothing but Newton, and the SI unit of area is nothing but meter square. Okay. If you divide both together, it will give the pressure. In table 6.1, pressure as a variable unit. In table 6.1, they give the units of pressure. First is the unit called as a Pascal. The symbol of Pascal is nothing but PA. Its value is nothing but 1 Newton per meter square. Okay. The atmosphere, second one, the symbol is ATM, and its value is nothing but 1 atmosphere equal to 101325 Pascal. And millimeter of mercury is nothing but a symbol of millimeter SI, and Pascal value is nothing but 133.3. Bar, nothing but symbol is bar, is nothing but 10 power 5 Pascal. Torque, the value of torque is nothing but 133.3 W Pascal, and pound per square inch is nothing but PSI decimal, and its value is 6894.76 Pascal. Okay, turn the page number 160. First, you should know the laws of the gases. Here, the Boyle's law. The Boyle's law is nothing but pressure volume relationship. Robert Boyle performed a series of experiments to study the relation between the pressure and volume of gases. The schematic of the apparatus used by him is shown in figure 6.1. By using the figure, Boyle explained about the law of gases. Mercury was added to the open end of the apparatus such that the mercury level on both ends are equal, shown in the figure 6.1. Add more amount of mercury until the volume of the trapped air is reduced to half of its original volume, as shown in figure 6.1. The addition of excess mercury is given by the difference in mercury levels on the tube. Initially, the pressure exerted by the gas is equal to 1 atmosphere, as the difference in the height of the mercury level is 0. When the volume is reduced to half, the difference in mercury level increases to 760 millimeter. Now the pressure exerted by the gas is equal to 2 atmosphere. It led him to conclude that at a given temperature, mark that question in public examination, the question will be asked like, define Boyle's law. The answer of Boyle's law is nothing but in page number 160. From the bottom, see the fourth line at the corner. At a given temperature, okay, at a given temperature, the volume of occupied by a fixed mass of gas is inversely proportional to its pressure. The volume of gas is inversely proportional to its pressure. Boyle's law. See the Boyle's law. Okay, the definition of Boyle's law is nothing but constant temperature, at constant temperature, this area, at constant temperature, the volume of gas is inversely proportional to its pressure. This is called as a boiling. The volume of gas, the fixed volume of gas is inversely proportional to its pressure. Okay, that means if you increase the volume, if you increase the pressure, the volume will be decreased. Okay, if you increase the pressure on a gas, it will decrease the volume. That is the meaning of Boyle's law. If you increase the volume, the pressure will be decreases, or if the pressure will be increased, or you can write also like this: pressure is inversely proportional to its volume. Both are same. Both are same. Okay. Volume is inversely proportional to its pressure, or pressure is inversely proportional to its volume. If you increase the pressure, volume will be decreased, or if you increase the volume, the pressure will be decreased. Okay. The volume of gas will increase, the pressure will automatically decrease. Then only the volume of gas will increase. Okay. Let's see. This is nothing but the Boyle's law. Okay. Let's see. At a given temperature, you should not change the temperature of the gas, which is obeyed by Boyle's law. Okay. At a given temperature, I repeat once again, at a constant or given temperature, the volume of gas is inversely proportional to its pressure. Or at a constant temperature, the volume of pressure, the pressure of gas, okay, the pressure of gas is inversely proportional to its volume. You can write both this formula, both this expression, both are same. Okay, for Boyle's law. Let's see. If you want to take the proportionality here, you have to add one constant, that is nothing but V equal to K is nothing but constant in K 1 by K. Okay, K is nothing but constant, V is the volume, P is the pressure. Okay, let's see. K is the proportional constant. When you arrange the equation, if you rearrange this equation, you will get the answer of PV equal to K. If you PV go to the left hand side, it will convert as a multiplication. PV equal to K into 1 is nothing but K1. PV equal to K. Okay, by rearranging the equation, we get the value of PV equal to K. Nothing but Boyle's law. Okay. Boyle's law is applicable to all the gases regardless of their chemical identity. Chemical identity provides the pressure aspect. Therefore, for a given mass of the gas under two different sets of conditions at constant temperature, we can write it. If we have two gases, two different gases, we can write the formula like this: K equal to, for first one gas, P1 V1 and equal to P2 V2. P1 V1 equal to P2 V2. Okay, let's see. Here the PV relationship is nothing but the gas relationship of pressure and volume of gases. Okay. The PV relationship can be understood as follows: the pressure is due to the force of the gas particles on the walls of the container. If the given amount of gas is compressed into half of its volume, the density is doubled, and the number of particles hitting the unit area of the container will be doubled. Hence, the pressure would be increased. If you give the pressure to many gases in a container, if you have a container, the gas will be located. If you apply the pressure on the gas which is in a container, the total amount of gas will be halved. Due to the pressure, the particles get closer to each other and very fast into the container. So in that case, the pressure of gas will be doubled. Consequence of Boyle's law. In page number 161, consequence of Boyle's law. The pressure density relationship can be derived from the Boyle's law as shown below. Make a note. Note that consequence of Boyle's law, it is nothing but the pressure density relationship can be derived from the Boyle's law as shown in P1 V1 equal to P2 V2 is nothing but Boyle's law. If you apply the Formula of volume nothing but m divided by d. M is nothing but mass and d is nothing but the density of the gases. Okay. Let's take the consequence of Boyle's law. Let's take the consequence of Boyle's law. Boyle's law is nothing but at constant temperature. At constant temperature, the volume of gas is inversely proportional to its pressure. Okay. Finally, we get the answer of X. V equal to proportionality divided by V. You will the answer also KV PV equals to. If I have more than one gases, the formula will be like P1 V1 equal to P2 V2 equal to P. This is nothing but the Boyle's law equation. Okay. If you derive the relationship between the pressure and density, the formula will be like P1 V1 equal to P2 V2. Here, the V is nothing but the formula of what? Mass divided by density. Okay, mass divided by density. Here, the mass of both gases are same, so you should not put any one in the formula. We can apply this formula P1 equal to m divided by d1 equal to P2 into m divided by d. This is the formula after applying the value of V. Okay, where it is the mass d1, where it is the mass and d1 d2 are the density of gases at a pressure P1 and P2. Here, if you rearrange formula, we can cancel this m. By rearranging the formula, we will get answer of P1 d1 equal to P2 and d2. This is the consequence of Boyle's law. Okay, this is the consequence of Boyle's law. In other words, the density of gases is directly proportional to its pressure. The density of gases is directly proportional to its pressure. That means if you increase the density, the pressure will be also increases. If you increase the density of gas, the pressure will be also increases. Okay. Let's see in one. In a figure 6.3, let us find the missing parameters volume 6.3 and B. In figure. Okay, in figure it will give the some relation of examples. You will see in the road calculation. Okay. Page 161. The book will give the some examples. In that we have to find the pressure of the gases which is given in a parameters. Okay. Let's take a page number of 162. It's nothing but a Charles law. Charles law is nothing but, this is called as a Boyle's law. Boyle's law is nothing but at constant temperature, the volume of gas is inversely proportional to its pressure. This is called as a Boyle's law. For Charles law, the relationship between the volume of gas and its temperature was examined by Gaseous Charles. We observed that for the relative mass of the gas at constant temperature, let's see that at a constant temperature in Charles law. Okay, at a constant temperature, the volume of gas is directly proportional to its temperature. The volume of gas is directly proportional to its temperature. That is nothing but the Charles law. Okay. Charles law is nothing but at constant temperature, at constant pressure, at constant pressure, the volume of gas is directly proportional to its temperature. Here, the meaning of this is nothing but if you increase the temperature of gas, at the same time the volume also will be increases. Okay, if you increase the temperature of the gas, at the same time the volume also will be increased. This is then known as the Charles law. Without changing its condition like pressure, at constant pressure, okay, at constant pressure for Charles law, at constant pressure, the volume of gas is directly proportional to temperature for Charles law. And for Boyle's law, at constant temperature, the volume of gas is inversely proportional to its pressure. Here, if we increase the volume, the pressure will be decreases. And here for Charles law, if we increase the volume, if we increase the temperature, the volume also will be expand. Okay. If you increase the temperature of any gases, it will expand. Okay. Let's see. If the temperature of gases increases, the volume also increases in direct proportion. So that V is divided by T is a constant. For the same system at constant pressure, one can write here the same system as you taken in your boil system. Okay. We can, if you want to remove the proportionality, you should have a constant nothing but K T. The formula of the derivation of V equal to K equal to V. K equal to V by 2. Okay. For more than gases, you should write K equal to V1 divided by V1 equal to V2 divided by V. Okay. Yes. For example, if a balloon is moved from an ice cold bath to a boiling water bath, the temperature of the gas increases. As a result, the gas molecule inside the balloon moves faster and gas expands. Hence, the volume will be increased. Okay. To take a two container, one container will be filled with the ice water and one container will be filled with the boiled water. Okay. Take a balloon with a filled air. Take a two balloons with filled air. Keep one balloon in a cold water and keep one balloon in a hot water. The balloon which is present in a cold water will be aggregate due to the coldness. Okay. If you decrease the temperature of gas, it will decrease, and if you increase the temperature of gas, it will increase. If the balloon present in ice water will be aggregate means it will be aggregate due to the temperature decreasing in a gases which is present in a balloon due to the presence of cold water. Okay, the balloon which is present in a hot water, the gas will be expanded which is in a balloon. Okay, because the boiled water will increase the temperature of gases which is present in its balloon. Let's see. Variation of volume, temperature and constant pressure. The plot of the volume of the gas against the temperature and the pressure shown in the figure 6.5. From the graph, it is clear that the volume of gas linearly increases in the temperature. See the graph which is given in the 163, 6.5. In this gas, if you increase the pressure, if you increase the temperature, the volume of gas is automatically increases. Okay, I should know already about that. If you increase the temperature of any gases, the volume of that gas will automatically increase, will automatically expand. Expand means nothing but increases. Let's see. V equal to UT plus C, where T is the temperature of degree in degree Celsius and M and C is nothing but a constant. When T equal to 0 degree Celsius, the volume becomes V0 and hence V0 equal to C, and slope of the straight line M is equal to delta V by delta T. Delta means nothing but changes. Okay, changes in volume and change in temperature. Delta V is nothing but change. Delta V is nothing but change in volume. Change in volume. Delta is nothing but the change. Okay, let's see. Therefore, the above equation can be written as the following: V equal to delta V by delta T into T equal to plus V0. V0 is nothing but the volume before the temperature of before the increasing the temperature of gas. Okay, yes. Here the Charles law Charles found that the coefficient of expansion is approximately equal to 1 by 273. Means that at a constant temperature for a given mass, for a given mass, for each degree rise in temperature, all gases expand by 1 by 273 of the volume at 0 degree Celsius. All gases simply expand at 0 degree Celsius, the volume of 1 by 273. Okay. Let's take the page number 164. If we extrapolate the straight line in figure 6.5, the graph which is present in 163 is nothing but shows that is nothing but if you increase the temperature, the gas will automatically expand. That is, the volume of gas will be increases if you increase the temperature. That is called as Charles law. Okay, the Charles law. I am repeating once again. Boyle's law is nothing but at constant temperature, the volume of gas is inversely proportional to its pressure. This is called as a Boyle's law. Okay, the Charles law is nothing but at constant pressure, the temperature of gas is directly proportional to its volume. Directly proportional to its volume. If you increase the temperature of a gas, it will expand or it will increase the volume. Okay, let's see there. Page number 164. The example is given there. Okay, the example is given there for example. It will be clear in a road friction class. Okay, let's see that 164 page number 6.2.3. Gaseous law, pressure, temperature, resistance. Joseph Gaseous stated that at a constant volume, the pressure of a fixed mass of a gas is directly proportional to its temperature. If you increase the pressure, the temperature also will be increases for Gaseous law. Okay, for Gaseous law, for Gaseous law, at constant volume, okay, constant volume, the pressure of gas is inversely proportional to is directly proportional to its temperature. The pressure of gas is directly proportional to its temperature. That is nothing but if you increase the pressure of gas, now for that gas, the temperature will be increased. Okay. Or if you want to remove the proportionality, you have that constant P equal to K into T. K is nothing but constant. If T is go to the left hand side, the T will be like that. P divided by T equal to, or it can write like this. This is called as Gaseous law. Okay, Gaseous. If P1 and P2 are the pressure at temperatures T1 and T2 respectively, then from Gaseous law, if you have that more than one gases, like if you have two gases, the pressure and temperature will be like K equal to P1 T1 equal to P2 and P2. Okay, let's see the 6.2.4 Avogadro's hypothesis. Avogadro's hypothesis is that equal volume of all gases under the same condition of temperature and pressure contain the equal number of volume. Underline the sentence. Avogadro's hypothesis. Avogadro's is nothing but Avogadro's hypothesis nothing but the equal volume of all gases under the same condition of temperature and pressure. The equal volume of all gases under the conditions of same temperature and pressure contains the equal number of molecules. If you have two gases like carbon dioxide and nitrogen, okay, if you have two gases, the conditions of the two gases are same, like temperature and pressure. If you have two gases, the conditions of two gases are the same. Then we have the same molecule of gases, which is present in carbon dioxide and nitrogen. We have same number of molecules, which is present in carbon dioxide and nitrogen. Okay, this is called as a Avogadro's hypothesis. Avogadro's hypothesis is that equal number. I repeat once again. Avogadro's hypothesis that equal volume of all gases under the same conditions of temperature and pressure that contain the equal number of molecules. The mathematical expression of Avogadro's hypothesis may be expressed as a V is proportional to A. V is proportional to A. That is nothing but the same volume. If the volume of gas increases, the number of molecules also will be increases. Okay. Avogadro's hypothesis. Avogadro's hypothesis. If the volume of gas increases, at the same time, number of molecules in gas also increases. Okay. For our hypothesis, volume is directly proportional to the n. N is nothing but the number of molecules. N is nothing but the number of molecules. Okay, let's see. If you want to remove the proportionality, you have to have constant V equal to K in N. Okay, if n goes to the left hand side, the n will be V equal to N. If you have total gases, the formula will be like V1 N1 equal to V2 N2 equal to 3. Yes. Okay. Where V1 and N1 are the volume or number of moles of a gas, number of moles or number of molecules, both are number of molecules or number of moles. Okay. Number of, you can write number of moles. You can write number of moles. Of moles of gas, and V2 and N2 are different set of values of volume and number of moles of the same gas at the same temperature pressure. Okay. And remaining we will discuss in the next class. Okay. Thank you.